Welcome to this video lecture recapping last week's material. I'm actually just going to recap Cauchy sequences for you rather quickly. We're going to go over the definition, the outline of the proof of a Cauchy sequence from the definition, and then I'm going to go over an actual example that will be similar to what you have to do on the individual homework. So we say a sequence of numbers is a Cauchy sequence. So this is what we define if for each epsilon greater than 0, there exists a number n such that m and n greater than n, and it can be greater than or equals, implies that the difference between Sn and Sm, that's Sn and that's Sm, that difference is then less than epsilon. So this was step 1 in a proof. Step 2, you could say this is really, you're saying for all m and n, so there's your other logical quantifier. There's step 3, and then there's step 4. So I'll outline the proof. We recall that we said this was very much like the definition for convergent sequence, except in that definition, we start with there exists a real number s, and that goes there. That's where we would put the s. And so basically, we're removing the need to find a limit and just compare the difference between terms in the sequence, conditioned on the fact that the terms are taken far enough out beyond some n in the sequence. So with that being said, the outline of the proof follows naturally. We see basically there's going to be 4 steps. There's no optional steps here. The first step, you're going to write something like let epsilon be greater than 0. Step 2, you're going to say, hey, choose n, and it's probably going to be greater than like some sort of function of epsilon, just like in convergence. And then step 3, you're going to say let n and m be greater than or equal to n, and typically say something like, and without loss of generality, assume m is greater than n. That's a terrible m. Let me fix that. M is greater than n. And this is just so, this is trivially true. If you take the difference between the same term, Sn and Sn, then it's just 0. So you're just interested in when they're possibly different. And so you might as well say, well, I'll let m be larger than n, because whichever one is chosen to be larger than the other is somewhat arbitrary. So let's go ahead and just use the convention that m is strictly greater than n. And then you would say something like then, and then in step 4, you would take, Sn minus Sm, writing what that is, and then, do the work that you would, kind of summarize from your scratch work to show that that is ultimately less than epsilon. And so just like with convergence, all the work comes down in choosing the n. We do it in a very similar way. We start with this type of difference. We work to simplify things until we get, usually with this assumption, some sort of condition on the n that then allows us to choose the capital N for everything to be small. So we did this with a series where I'm going to show you an example that's much like your homework. So I'm looking at exercise 8.2, and I've just repurposed the problem to say, hey, prove the following sequences are Cauchy. And I'm going to show you how to do it for part C. It's a good exercise for you to do this for all the others. And then there's some particular problems I'm having you work on the homework. But the more exercise, the more practice you have with this type of definition and these proofs and this machinery, this algebra, the better. So here's some good examples to work with to just prove that they're all Cauchy. Well, let's go through the scratch work. So our sequence of terms is 4n plus 3 over 7n minus 5. And so in my scratch work, I'm just noting I'm going to let m be greater than n. I'm going to switch to a red pen so that it stands out a little bit more. I'll make it fat too. And so my sequence terms are Cn. So I actually am using Cn minus Cm. And I generally do it in that order. It doesn't really matter. And so then I have this difference here. I just write in what it is. Each sequence, here's the nth term, here's the mth term, right? So Cn, Cm. And then you go through algebra, and there's just finding a common denominator and working everything out. And that's all that's going on in these 2 steps. So there's a lot to read there. You can kind of pause the video to see it. I'm not going to dwell on it. It's algebra. But a lot of terms cancel. And what's specifically like that term cancels with this one, negative 15 and 15 cancel out. And I'm just left with, 21m minus negative 20m. So that would give me 41m. And then similarly, I get negative 41n. And so then I say, well, look, that's just 41m minus n. And I can drop the absolute value because m minus n is greater than 0 because I'm letting m be greater than n. That's one of the things you do so you can get rid of the absolute values. And also the terms in the denominator are also positive for all n and m greater than 1. So then I have this term and I say, okay, I need to start simplifying. Well, I can immediately drop the n in the numerator because m is greater than m minus n since n is greater than 0, right? So I'm not writing that justification out. I think that one's pretty obvious. But then this is still too complicated to work with. I have m's and n's, and the goal is to simplify to just n. So I say, well, look, 7n minus 5 is always greater than or equal to n. 7m minus 5 is always greater than or equal to m, as long as n and m are both greater than or equal to 1, which they are for this sequence. So then I can replace the denominator terms with just n and m to get this expression. And then you see the m's cancel out immediately. And that leaves me with 41 over n. And I say, well, look, n is going to be chosen greater than or equal to capital N. So that's going to be less than or equal to this. And then it tells me, oh, yeah, that's how I have to choose capital N to be greater than 41 over epsilon. So very similar scratch work, maybe a little bit more algebra involved because we're not just taking the difference of some number like in convergence. We have a difference in m, but we're ultimately getting to like the same thing. So then the proof looks something like this. I'll just put the whole thing up on the screen. Here's our 4 steps. Oh, I didn't number this. This is all step 4. So the first step is, hey, let epsilon be greater than 0. Again, nothing complicated. Look at step 2. We choose n to be greater than 41 over epsilon, and that makes epsilon greater than 41 over n. Again, this is somewhat optional, but it's nice because it really says what's going to happen down here when we go to the final step. Okay, let n and m be greater than or equal to n, and without loss of generality, assume m is greater than n. Then, and so then this is all step 4. I'm just recreating the relevant parts of the scratch work while removing some of the more annoying details that you would assume senior level student in analysis could do. So I always write out the actual terms I'm working with. This is the Cn minus Cm. And then I just assume that somebody can work out the common denominator and cancel terms and understand they can drop the absolute value, but I'll tell them why, because m minus n is greater than 0. So this whole thing is greater than 0, so it's okay for me to drop absolute value. So I think that's pretty sufficient. And then I make the simplification in the numerator, and of course then there's the greater than, less than or equal. In fact, the strictly less than. This term is strictly less than that one. But then this kind of got screwed up a little bit. Let me fix the font on this. This is the n times n is there. I don't know why that shifted. So go back to the red. And sorry if you picked up I guess I just got an email. My internet browser is open. So then we saw this term before, and I justify the simplification of the denominator, and then I've canceled the m's, which is pretty obvious, doesn't require much statement. So then I have this is equal to 41 over n, and then we finish the proof. So pretty similar to what we've seen before, and you should have hopefully seen that coming from the scratch work. So that's it for this recorded lecture. Good luck with the homework and practicing with the definition of Cauchy sequences.